Okay.
Okay.
Today, wait, not okay. Sorry.
Oh man, how am I supposed to keep track? I feel like we're missing people.
Oh yeah. Jay.
I miss you, Jay.
Sick leave. Glasses
Jay,
hurt.
Gideon,
Jay Nish was missing?
Jay's here.
Brian.
Brian.
I mean, Brian.
That's weird. Eric's gone.
All right, as long as Dan is here, that's all that really matters. All right. David, go ahead.
Okay, so it's find the directional derivative of the function direction u cosine.
Okay, so,
Well, the way I was understanding to do this was, in the way I got to this solution was by taking the gradient of this function and then plugging this into here and dotting them. But
Good.
it's saying that was wrong.
okay, let's do it. I think we did one similar to this. I'm not sure if it was the exact one. Go ahead, give me the function.
Okay, so the function is f of xy is equal to y over 3x plus y. And then theta is equal to negative pi over 6.
Okay, what we want,
The u, or the unit vector is cosine of plus sine.
yeah. Okay, that's usual for any unit vector. As long as we have a theta here, we know what the unit vector is. We know what direction we're trying to go in. The unit vector is going to be cosine theta, sine theta. Okay, as long as we have theta. Now we have to do cosine of the opposite of pi over 6 and negative pi over 6. Cosine of pi over 6, square root of 3 over 2. But the negative pi over 6 will place it in the fourth quadrant. And given that that cosine is in the fourth quadrant, is it going to be positive or negative in the fourth quadrant?
Positive.
Positive. That away. Square root of 3 over 2. The sine of pi over 6 is 1/2. The negative pi over 6 places it in the fourth quadrant. The sine is going to be
Negative.
negative.
I just did this problem at homework.
Good deal.
Still.
Okay, so that's our unit vector. Next, we're going to have to find the gradient, because the directional derivative is a combination. It's the dot product of the gradient, the directional derivative in the direction of this vector u of our function is equal to the dot product of the gradient with our unit vector. So we're going to have to find the gradient. This is what you said. The gradient, partial with respect to x, partial with respect to y. Partial with respect to x, probably the best way.
3y over
Negative 3y, 3x plus y squared on the bottom.
Yeah, and did you say negative in the front? Yeah, wow, very nice, wow. Just what Liam said. All right, here we go. Yeah.
So when they ask for like the gradient times the like a normal vector, like a normal vector of u, like what does that give you?
This dot product here, this gradient times the unit vector u in the direction of our angle, gives us a directional derivative. What does it give you geometrically? You've got a surface, you've got a direction, okay? In that direction. If you were to take a plane in that direction, plane perpendicular to the xy plane, that contains that unit vector and contains the point in question, okay? Because you've got planes that are parallel to each other, but you need the plane that contains the point in question. Oh, wait, where's your point? They give you a point?
No.
No, so we have to do this in terms of any x and y.
That's what I was
Apparently.
saying.
All right. So, anyhow, take this. Is that?
That looks really messy at the end.
Oh, really?
Yeah.
Yeah, we can do it. Okay, you've got a plane that intersects our surface at this point in that direction. That plane's intersection with the surface will give us a curve. Okay, a curve like this at this point. The slope of the tangent line to that curve at that point, okay, is the directional derivative. It's the slope of the tangent line in that direction. Okay. If we were to take another direction, say this way, okay, parallel to the y-axis, say, that would be a partial derivative with respect to y, we'd get another curve. The slope of that tangent line would be the directional derivative in that direction. If you take all the directional derivatives, all the tangent lines, you're going to get, what would you get if you took all the tangent lines to the surface at that point in all the directions? You get the tangent plane. That is correct, yes.
So if you took the normal vector from that vector u and did the dot product of the gradient, would that directional derivative be normal to?
No. Okay, hold on a second. You're not taking a normal vector. You're taking the unit vector in the plane pointing in the direction that we're going. That's not the normal vector.
Oh, I meant, okay, so when you do the when you're dividing by the magnitude of that vector, that's giving you a unit vector?
That's giving you a unit
Okay,
vector.
okay.
But the thing is this. If you write the unit vector in terms of cosine sine, it's automatically a unit vector. See, they gave him an angle, and they said, okay, find the directional derivative in that direction. If you make this, take that angle and put it as cosine sine, like I've done it here, we automatically have a unit vector in that direction. Usually what happens is they give you a vector in the xy plane for your direction. Suppose they gave us the vector v as 3, 4. That's a direction. We'd have to turn it into a unit normal, divide by its magnitude, like you just said. So it'd be 3/5, 4/5. And then we would do the same thing we're doing now. Okay, you with me on that?
Yeah.
The normal vector is a little bit different. If we want to find the equation of that tangent plane we just mentioned, what we would do is what we're going to do for the lab. Okay, we would change our surface into a normal level surface for a fourth dimensional object, find its gradient so that we have a normal vector to our surface, and then use that normal with the point to find the equation of the tangent plane. And we're going to do that in a little bit. Yes?
So when I was doing it, I got the unit vector, so I divided by the magnitude and it came out to be 1.
Yeah, that's always going to be the case when you put it in this form. As long as they give you an angle, and if you put it as cosine sine, you've got a unit vector automatically. Okay, all the time.
So what does the scalar quantity represent at the end when you dot product the gradient and the unit vector
When you take this dot product here, that gives you the slope of that tangent
in that direction?
in that direction. That's exactly what it is. It's a real number that's a slope of the tangent. Yeah. All right, this is good. Let's do it.
I'm excited.
What's that?
I'm just pumped. Can't wait.
Oh, okay. Anyway, Teddy. All right, partial derivative with respect to x. We're going to do what Liam just said. Consider this as y times the quantity 3x plus y to the negative first. Take that derivative. The negative 1 comes out, multiplies by y. Then you get 3x plus 1 to the negative second. And then times the derivative of 3x plus y, which is the 3. So you end up with a negative 3y 3x plus y squared. Okay? That's the partial derivative with respect to x. Oh boy, okay. Now we got to take the partial derivative with respect to y, and we've got a quotient rule here. I don't see any easy way of doing it. I just got to do the quotient rule. Okay, denominator.
You get like denominators though, obviously.
What's that?
You end up getting like denominators, obviously.
Yeah. Yeah, well, that's true. That's nice. All right, denominator, derivative of the numerator. We're taking the derivative with respect to y now. Okay. Minus numerator times the derivative of the denominator with respect to y. All over denominator squared. So we do have common denominators here, so that's nice. Okay. So that's equal to negative 3y over 3x plus y squared. And we drop the grouping symbols, the y's will cancel. We'll get a 3x over 3x plus y squared. Okay, that's our gradient. Is that what you got?
Yeah.
Ooh, okay. All right. So, the directional derivative, the slope of that tangent line to our surface in that direction is equal to the dot product of this with that. And we're going to get this times this, negative 3y square root of 3 over 2 times 3x plus y squared, okay, plus this times this, so that becomes a minus 3x over 2 times 3x plus y squared. This 2 we get from here. Okay, same thing over here. And then, at least we have a common denominator. That's helpful. So we end up with a negative 3y square root of 3 minus 3x over 2 times 3x plus y squared. Well, I mean, I could factor 3 out, but that doesn't really go anywhere.
That's all I did.
And they give you credit right at this point?
Yeah.
All right, so Dave, what would you do?
Something else.
Something else. That'll do it. Put that in.
Wait, Burns, where did the square root of 3 come from there?
That-
These
The moment after you submit it.
That square root of 3 came from, back here at the cosine of theta.
yeah, that's the,
Did it come out okay?
Yeah.
Good. All right, any other questions at all? All righty, hey, let's take a look at the lab. Here we go. Oh, wow, this room is the best room on the whole floor.
Do you guys have to switch rooms every like semester, or do you get to like keep it?
Well, some people get their own room. Z gets this room. It's his room.
You get pretty vicious when you guys are picking rooms.
Yeah, well, this room is obviously really nice.
this thing is like pretty important.
Z-Man, Z is important. He is important. He knows things. He's important. He deserves his own room. I totally agree with that. I have no complaints. I'm in this room. I'm in where used to be the Mac lab over there, and that's fine with me. As long as I have this room for my Calc 3s, that's all I really care about.
Burns, all you have to do is what Z does, ask for a projector, ask for a certain thing.
Yeah, but if there's a direct conflict, if I say, well, I want this room when Z wants this room.
No, I'm
I
saying
already
it's
did
that
this.
Oh, that room? Yeah, well,
I'm
that's
sure
true.
needs a copy.
That's true. All right, but anyhow.
I think it's good.
Let's take a look at this. What you're going to be doing in this lab is tangent planes.
Well, this is the end result of mine.
And here's the code for it, and you should be using it. So here's what we got. Here's the surface, 4 minus x squared minus y squared. And I think we've done things with this. It's a paraboloid. Starts up here at 0, 0, 4. That's the top. That would be the vertex. And comes down this way. Okay? This is what we have. Paraboloid coming down this way. And what we want to do is find the equation of the tangent plane to this at any given point. Okay? So, let's go through the code then here. I'm going to put it in and manipulate so we can change the starting position. Starting position being x sub naught, y sub naught. And I say, okay, let's let x sub naught be a and y sub naught be b. That way in the manipulate, what I'm going to do is change the a and the b. So it changes the initial position so we can move the tangent plane around the surface. I'm going to find the partial derivative with respect to x. Oh, and by the way, I did want to mention this from yesterday. There was a point in doing the pipeline problem when taking finding the critical values, when the k's were all the same, k, and k, instead of 3k, 2k, and 1k, and it gave me a null set solution there, and I got momentarily confused over that, why it didn't solve that. And the reason is, Dan and I figured out afterward, is that there is it's not a solution for the partial derivative, it's not a critical value, it was an endpoint, where you have to take the end of it, where they use the x to the n and the y to the n in order to go straight across. So there was no critical value there. It was an endpoint. So I just want to point that out. Okay. What's that? Oh, all right. But anyhow, I don't know if you guys noticed that, but when I looked at that, I said to myself, wow, that's pretty weird that it can't solve that. But there is nothing to solve there. It wasn't a critical value. It was an endpoint. So anyhow, I wanted to mention that. All right, here's the partial derivative, and what we're going to do is substitute for the x sub naught and y sub naught, That's what this notation means. Given that x is x sub naught, y is y sub naught. Find the partial with respect to y. Okay, that's what this notation does. And substitute the point in for x and y. And then find the equation of the plane. Well, you know how to find the equation of such a plane. We make it into a level surface, like we just mentioned, and take the partial derivatives for w. And what we'll get is a partial with respect to x times x minus x sub naught, partial with respect to y, y minus y sub naught, and the partial with respect to z, which is a -1, and substitute in for z. And this is what we'll end up with. And then plot. Do a 3D plot of the surface and of the plane. This is the surface, and this is the plane. Okay?
So
Yes?
you say the capital D next to f of x and y up there is like a function for partial derivatives?
It's exactly what it is.
Okay.
Oh, wait, and who was asking about that before? Oh, that was the guy in my Calc 1. All right, never mind. I forgot. It was in my Calc 1. But this is how to find the partial derivative of a function with respect to x, capital D. Okay? And you can use this notation for second partials as well. Did I actually prove it down here? No, I didn't. Okay, but that's okay. So, get the equation of the plane, get the equation of the surface, show them all, and then use manipulate to change the a and the b around. And so, if we start at the beginning, it's a little choppy though, but there it is, the x, and now the y at the beginning. And what is exactly the beginning? A is at -1.5, B is at -1.5. So it's over in the corner here. And then what we can do is change A, which will be the x, so we'll move it along the x-axis. This tangent plane. And then we can change the B, which changes the y starting point as well, and it goes around this way. I hesitate to animate this, but let's take a look at this. Let's make this a little bit bigger here. And let's animate it, see what happens. I don't know if the computer will... Oh, that's not too bad. That's kind of cool. All right, that's the x. A little bit of jerkiness here. And if we do the y one at the same time, it's going to
Do nothing.
do nothing.
Oh my god.
There it is. Going to the side. Oh, they're pretty much in sync though. Now it's going diagonally because the x's and y's are both changing.
It's like a live.
If one goes fast, well, I can slow down the y's here.
Got a program for life.
Yeah, you're making it breathe. I think you figured out some sort of new artificial intelligence.
Wow, that's pretty cool, huh?
Yeah.
You know what? Wow, that's pretty cool.
Hit the arrow at the last one twice.
Twice?
Yeah.
1, 2. So,
Give it a moment to change.
okay.
And do that for the X too.
The X one as well. Oh, make it go back the other way. Oh, so this is a continuous thing then. It goes front and back. Okay, instead of starting at the starting point. Oh, so this is better. This is better. This is better. this is pretty good. This is pretty good. I like. Yeah, this is better. Instead of going back to the beginning, this continues on. Now this would be cool if you started working for Roomba, right? Roomba with the vacuum, the robot that vacuums and it goes around. A way of functioning, way of programming the Roomba to go around the room and cover the room. You have to come up with a way to make sure you covered everything. But this is it. I mean, this is it here, right here. All right. So what you guys have to do? What do you have to do? I don't know what you guys have to do here. What do you have to do?
I'm curious, how do you write that manipulate up there?
How did I write it?
With the multiple lines of code inside the manipulate. I've never seen that been done.
This here like this?
Yeah.
You put semis at the end of each one to separate them. Actually, commas would work, I think, but the problem is with the semis are better because that suppresses the output, as you know, and I don't think we have a problem. You don't like the?
Well, no, I've never seen it. I've never seen it done that way.
It looks kind of nice because you can follow it better.
Do you not need a semicolon up to the show? Why do you do that?
If you do, I don't think anything would change after the.
No, it would suppress the
It
output.
would like.
I don't know. You think on a show? Hold on a second.
If you put the semicolon after the show, it would.
No, just the whole line.
All right, hold on. Oh yeah, no. All right, fine.
No, the rest of that line is part of the manipulate.
Yeah, the A and the B part are going back to the manipulate part. Yeah, these two guys are back to the manipulate.
That's crazy.
What are you using for next line in this? Because that would end the function if you just used enter.
What's that now?
How are you getting a new line in this?
I just hit return. Like this? Wait. So, this is kind of weird because these things usually line up and they're not lining up, but the thing is working perfectly. So who am I to argue with Mathematica that's working perfectly? But I see your point. But I just did a return and that's what we have.
I've never seen it formatted that way.
There you go. Maybe I'll write it in and send it into Wolfram. And maybe I'll get on there before you do, Dan. Just kidding. Just kidding. All right, what do you guys have to do? You got a couple surfaces to do yourself. Z equals 4 minus x squared in the tangent plane at a particular point. Then I want you to do z equals sine of xy. And please note, even though I've got the sine written as a lowercase s here, written in English, you know when you do it in Mathematica.
Do it the exact same way.
No, yeah, right. No, that's not the way to go. The way to go is use a capital S and square brackets to enclose the arguments. Please do that. And find your own surface and do a tangent plane and use manipulate to change the point. Very similar to what I just did, but you've got to come up with your own surface. That's all. Make it something interesting. Make it something cool where I'll say, wow, that's pretty cool. And yeah, and then get a 92 maybe. If you want a 93 on it, talk to Dan, see what Dan's doing. Actually, a 93 would be good. If you put the normal vector in there, and as the plane moves around the surface, you see the normal vector moving with it. That would be pretty cool. What's that?
100, I'll take nothing less if I do that.
100, huh?
All
All right, I'll have to think about that.
Like, I know it's impossible, but what could you imagine someone would do in order to get up past a 95?
Did you get a 96 in
Oh
something?
yeah, I've got a 96.
He's
Like
got
past
he-
that, past that.
Past that?
Yeah, like
100.
I don't think I've ever given anything past that.
I think you would have to write a new software that's
I know,
better,
I gotta tell
better
you.
than
If you
Mathematica.
design a new software, would you give him a 98?
Yeah.
Okay, that's fair.
Start your own company.
99, maybe.
Partial credit.
All right, you guys ready? Any other questions?
D&D.
Monday, what are we doing? I'll take any
Oh, that's
questions you have.
Tuesday.
Tuesday's test.
Yeah, math
Oh, go ahead.
Math club's on Monday. You just every Monday. You never get anything. All right, math club's on
Because we have to do it questions. Yeah.
No. Oh, on one. Yeah. My difficulties. You should get 98.
No, go away.
Oh, that's cool.
Well, I had, this is my.
Oh, that's the sign of exponential.
Wait, you only got
Okay, I just want to make sure I'm doing this right.
Doing it.
I know I got the
Yeah, Daly's almost done.
How'd it go? Is that all right?
I didn't get the problem. What was such a nice explanation deal is for that problem for the volume. Yes, I should divide by 2, but you gotta do literally close.
He's in Wilder. Wilder?
I show weekly I had 3 or 4 problems already.
Yeah.
No, it's all like 10. It's like he only
get ready
assigned
for
for like
going to
3 or 4
career
questions,
and
but
going
they're
to
like,
time
they take a long time.
60 hours.
Wow, wow, wow. What would you major be?
I was doing physics and astronomy, double major.
Really?
Yeah, so.
Wow, that's pretty impressive. That's pretty cool. They have good physics, astronomy at Mount
They have good physics, yes. Astronomy is a 5 college major.
Oh, so you go to UMass or Amherst or
Yeah.
something like that?
I was
Hampshire?
still taking the classes at Mount Holyoke because those were preliminary classes, but
Yeah.
as I would have gone into junior year.
Yeah, my daughter goes over to Hampshire for parties. That's what she does.
That's good too.
No, my daughter, she's a good student. She's a great student, but she's not majoring in any of the STEM things. She's majoring in international relations.
That's very good in Mount Holyoke.
Yeah, it is. I don't know what she's gonna, I don't know what the outcome of that's going to be, but she does want to study abroad too, so she's psyched about doing that, and she's a good student. She's a great student. She's,
She'll find her way.
yes, she will. I hope, yes. I hope.
Everyone in Mount Holyoke does.
You think so?
Yeah,
No,
everyone.
that can't be true. Everyone?
Everyone does.
All right, okay. You found your way then?
Well, sort of.
Sort of. Okay, all right. So you may come here first
Yeah.
before you're ready to go
Back.
back. All right, well, what math have you taken so far then?
I have taken Calc 3, but that was in
Oh.
my 3rd semester
Wow.
there. But as I said, like I did like sort of 2.5 semester.
Yeah.
So I didn't quite complete that semester.
Oh. Do you remember this stuff? Tangent
I
plane?
didn't go this far.
Oh, you didn't? Oh, you
No.
didn't make it that far. Okay, okay. Yeah, this is a good group. This is a great guys, and this is a good group. You know, they're all engineering majors, so they're serious students, and
Yeah.
we have a good time and stuff like that.
That's,
So it's
that's
good.
what I kind of wanted to see.
Yeah.
More than the coursework of the.
Yeah.
Yeah.
Cool. Well, hey, well, I wish you luck. I hope it all works out, whatever you decide to do. You know, so that'd be great. That'd be cool. Yeah? That's what you want to? Oh, good.
I would like him to graduate before I can go back to school full time.
Well, that makes sense. But
Yeah.
you guys obviously work it out and you talk about it.
Yeah.
Sure. That sounds like a plan to me. Sounds good.
Thank you so much.
Hey, no problem.